Hello, everyone. My name is Anat Kasfi. I'm the director of the Taskar Center for Accessible Technology. Thank you so much for attending the Ben Taskar Memorial Lecture today. I did forget to. So I'm so elated to welcome Dragomir Anguelov, who's really been pushing the envelope on use of machine learning in autonomous vehicles, really since 2016. So first at Zoox, and later at Google and Waymo. For an industry researcher, having 115,000 citations of academic papers is quite an achievement, and Drago is at that scale. At Google, he worked on 3D vision and pose estimation for StreetView, where he was the first to loop close the world with StreetView, and then led a research team at Google as well, which developed computer vision systems for annotating Google Photos. And his team won the 2014 Imagenet classification and detection challenges. With Waymo, he's been for the past 5.5 years and received many accolades, among which was the 2022 Motor Trend naming him Software-Defined Vehicle Innovator Award. Without further ado, we have a long talk, and he's going to tell us all about the Waymo fleet. I'm super excited to welcome Dragomir Anguelov.
Thank you, Anat, for the kind introduction and for the big honor to present at this memorial event for Ben Taskar, who was a close friend, and it's been a bit over 10 years since he tragically passed away, and 10 years in some way is not that long of a time. I hear say now we have a daily show with Jon Stewart, which we had then, and he loved the daily show, so some things don't change. So Ben was a brilliant researcher and also an amazing person, which I think a few of us who are here that know him can attest. And I think another thing these 10 years make me realize is you don't meet many people like that. And I cherish our friendship for the time that I was blessed to have it. I really got close and friends with Ben when we were grad students. So I was older, but I joined a group where he was young, but already doing fully fledged, capable, independent research. And as I was starting to do my work, he was doing already seminal work like M-cube nets and then many other papers, was incredibly hardworking and full of ideas. And we spent many all-nighters there working and listening to each other's music, and he's enduring my music tastes, and we were doing push-ups, and I got to see and get to be inspired by just the dynamic, powerful, motivated force that he was. But he also was a lot more than a brilliant researcher. He was kind, helpful, brave. He later on went on, he was a great mentor to the students, very approachable. He had a depth, had interests in literature, photography, poetry, hiking and traveling, and many, many beautiful, multifaceted aspects. So he went on, then of course, I was following his work closely. He went on to a couple of universities, delivering many more seminal papers, and succeeded in many fields. So I was a computer vision perception researcher, and he started in general ML, probabilistic graphical models, and natural language processing, and then in computer vision, where I was, he still delivered multiple strong works. So he mastered all these fields. And around the time, so I met him maybe 2 or 3 weeks before his passing, and he was full of drive to help accessibility space and how he was going to build a motorized wheelchair and how the best eye tracker ever. We're always trying to say we'll build the best something ever. And I wish he got to build these things. I think now I'm in this space with Waymo where we can affect mobility for people. And so hopefully I can contribute some difference to this space that was dear to him. So I'll start my talk. I will tell you a bit about Waymo and some of our work in machine learning. I lead the research team at Waymo. We're Alphabet's autonomous technology company. And our history is long, so it spans these two phases over 14 years. The first phase was proving that autonomous driving can be done and it can be safe. We deployed we did the first fully autonomous drive in a car like this Firefly in 2015 in Dallas, and then took several more years to get ready for a public-facing service, which we launched in 2020. And that was called Waymo 1. And since then, we're in our second phase where we try to bring this service to more and more locations and to more and more customers. In the last 3 years, we have scaled to 225 square miles in Phoenix metro area and the entire city of San Francisco. We deliver tens of thousands of rides every week to paying customers, rain or shine, 24/7 in these locations. And our experience has been enthusiastically received by a lot of people, and you can go to these cities and experience it. We are expanding next to Los Angeles and Austin, Texas. In Los Angeles, we're already giving rides in select areas, fully autonomous. And here's some example of the driving that we have been doing. This isn't just a few examples. This is us driving a tunnel in San Francisco where pedestrians are walking in the middle of the road. This is us driving in reasonable rain. Maybe not by Seattle standards, I'm not sure, but still. And there are more cases. On the top, you can see the lighter points, and the cars and pedestrians are parsed in different colors, but we use 3 different sensors, camera, lidar, radar. Here it is us interacting with signals by a construction worker. Here is on the left, you will see some other interesting case. Also construction, this person holds a stop sign but tells it to go, so we hesitate a bit, but then we follow the instruction eventually. And in San Francisco, there is a lot of narrow roads and navigation. And in this case, I think you need to go and pass this person going outside of the vehicle. You could see the lights going. And then there is negotiating with other road users, both vehicles and pedestrians, motorcyclists, scooters, segways, many cable cars. Here, you can see that San Francisco is a hilly city. Sometimes vehicles are occluded because of elevation. On the left, someone decides to double park. We need to stop in a reasonable way, let them do their maneuver and proceed on our way. So maybe give you some idea of the kind of situations we regularly need to handle. So autonomous vehicles can also play a significant role in shaping transportation equity and to bring benefits to mobility-challenged people.
A really significant challenge of being blind is the issue of transportation because I can't drive. I need to rely on others for that basic requirement of life.
I can do everything for myself. The only thing that I cannot do by law is drive a car.
I was diagnosed with epilepsy at the age of 8.
People with epilepsy are told no a lot. No, you can't go to that party. No, you can't be in the sun too long. No, you can't drive.
Usually I have to get rides from like my sisters or my parents.
The idea of having autonomous vehicles is life-changing.
You can open a lot of doors, not just practically, not just, oh, let me go shopping, but also emotionally. Also like, okay, I'm not dependent. I'm not relying. I'm not a burden on somebody else. I'm my own person. I'm doing my own thing.
I live with MS, so I myself don't have a disability, but I've met a lot of people that do, and I know a lot of them would benefit greatly from something like this.
I'm thinking about my own child. She has a secondary diagnosis of cerebral palsy, And I would like there to be technology for her available so she can get that independence.
The chance to have autonomy in vehicles and everywhere else is a mean to get us to where we want to go, which is being part of the world. It's not just about going to a place. It's about having possession of your own life.
It's providing a platform for us to be able to travel independently when and where and how we want to. It's just priceless.
今年80岁，对市民来说，这当然是很方便，特别对一些老人。
I have a spinal cord injury. I was injured 12 years ago, so I am now a wheelchair user. We love when we partner with technology organizations like Waymo. Waymo is doing an amazing job at making sure that they understand our needs at the development phase.
This technology can provide a life without limits.
It could add that freedom that I don't have. From a self-esteem level, that'd be great, and from a practical level, it could be life-changing.
It's a new sense of liberation. That's why it's so special. It's about freedom.
So a couple of years ago, we launched the Waymo Accessibility Network. We partner with different disability advocates and organizations who share in the mission of improving access to mobility in communities. And we have also mapped out our Waymo experience to make sure that it's available to more people with disabilities. And we develop features in our service, in our app, to let people with who are blind or hard of seeing or hearing and otherwise to be able to use our vehicles. And just a few examples. So we have an accessible app that supports screen readers and high contrast. Deaf users are able to contact our rider support team with the chat feature instead of a voice call. There are braille buttons in the car. We display on top of the vehicle the initials of the person in bright colors, so you don't need to read license plates if you're vision impaired. We allow you to push a button to honk the vehicle if you want to know where it is. There are audio tools that explain to people who cannot see well the screen what the vehicle is experiencing. It's yielding, it's stopping at a sign, to give you more context of how you are driving. And we found that some of these features that we developed for people with disability also help the general population as well. And for wheelchair users, we have mapped out the needs across the experience. And we hope to use this to inform future versions of the vehicle. Our current vehicle cannot fully support the need of wheelchair users. However, we offer a service with the same Waymo One territory and app and ease of hailing, where a partner company will come and still pick you up and drive you if you're in a wheelchair. They are accessible through our app. With regards to mobility, I'm also encouraged by our capability to automatically map accessibility features of an area in high definition. We can aggregate image information captured by our vehicles and annotate it with machine learning models semantically, as well as LiDAR information captured by a vehicle and annotated with our models semantically. And we can combine all this information in a consistent semantic 3D model of the static world. And it looks a bit like this. So the left side shows the 3D reconstructions of the environment, mostly with the natural colors as obtained from the camera. On the right, you see the semantic classes of the various objects that correspond to the reconstruction in 3D. So you can see, for example, the signs in red and traffic lights in yellow and various obstacles in one kind of brown. But you can also see dark blue. These are curbs. Here, the greenish thing is mostly a driveway. Everything is mapped in centimeter resolution. And you can see all the kind of lighter blue things are walkways and so on. So from this dense data, it's possible to process and potentially reconstruct accessibility features like where are the curbs, how big of a maybe wheelchair can cross what areas, what is the grade. So personally, I'm hopeful that with technology like this in the future, we can enable accessibility improvements and partner with the cities that we have deployed our service in. Now, let's get back to the main topic of my talk, which is our work on using machine learning for autonomous driving. The first slide is, okay, let's explain the problem with autonomous driving. You have different sensors on the vehicle. In our case, 3 different kinds. I think different companies and approaches may use different subsets of these. And so you go from sensor observations of the world. You build this driving agent that then applies steering and acceleration and drives the car. Right? So what is the difficulty in building this driving agent? One, it's a safety-critical application. You need to be safe and robust. There is extremely low tolerance for errors. There are real-time latency requirements. Often you might need to process the information and react in 10 hertz or faster. You are compiling very high-dimensional input. So it's very complex high-dimensional inputs. You have at least a dozen sensors. You have maybe hundreds of millions or more sensor readings, camera pixels, LiDAR scans, and so on per second. And you usually need context of multiple seconds sometimes to understand the details of a scene. So you have all this data. You can imagine this huge tensor of all this data. And now you need to learn from that, from what you observed, how you drive. And in that tensor is things like different types of environments, urban, suburban, freeway. There's different conditions, different weather, time of day, and seasons. There is complex environment context that we humans understand, but the vehicle needs to understand, like people with the gestures, construction, at intersections, the rules of the road, sidewalks, and so on. So there is rich context that needs to be understood in order to drive well. There are also rare events. So what I showed you before maybe are not too rare events, but here is things like barbecue grill falling from a pickup truck. It's 64 miles per hour. There are houses driving in the street. There's people walking around holding signs. And there's even much more rare things. But I think this gives you the idea. And therefore, it's hard to build an agent that handles this large variety of cases and enter ML, right? So ML is very promising to help to facilitate and make it easier to build such an agent. Why ML helps? We can learn from the rich data that our AVs collect. How do we learn? Well, we can understand and predict what happens in the environment. That's a rich training signal. Even more pointedly, we can learn from the human driver demonstrations. So in the world, we observe humans drive, and a lot of them drive well, or it's either the drivers, we have to drive our cars, we can watch how they drive, we can watch how other people drive in the street as well and learn from that. So that's a very rich trove of data. And then the question is, okay, well, we want to help with ML, so now what is the challenge? The challenge is generalization. So essentially, how do we learn the most from the data you have? Subject to compute and budget constraints, right? And that's our problem. And a lot of our talks that I've been giving over the years is scaling, driving, you can call it perception, planning, or with ML, right? And that's the game. We want to go as far as possible towards leveraging our data to design a good agent. There's a second problem, which I won't talk as much today. So it's not just the agent, but then once you have the agent, you need to test and convince yourself it is robust and safe and performant. So you need then, what do you need to do that? Well, you can drive in the real world with operators, but it's hard to do at scale. And it's not always the safest, especially for difficult, rare, risky maneuvers. So you need a simulator for scalable system validation. So what does it need to do? You should be able to replay scenarios you drove and see how you react in these scenarios, maybe given a new planner or some changes you made. You can generate new scenarios that you've never seen before, but test corner cases that maybe you were not able to exactly collect. And what's really interesting about our autonomous vehicle domain, it's multi-agent. So all this simulator and all our driving is also dependent and conditioned on how we interact with the other road users, whether they're pedestrians, vehicles, and so on. And so it's difficult to also build such a simulator. So we want to build the simulator as much from the data we collect as possible as well. And so it's a similar problem of generalization. How much can I facilitate the building of this simulator by using machine learning? So that's the sibling problem to let's build the driver. We also want to build a simulator. So these are the topics we usually work on. Now today, in this talk, I will present some of our research that covers aspects that we found helpful in building the scalable ML stack or generalizing agent. And when you start this talk, the first topic is, well, naturally architectures. So first, I'll give a description of what an autonomous vehicle architecture looks like. So you have the sensor data comes in. There's a perception module that typically what we found works in the perception module is from all these sensors, you aggregate them in a coherent representation, which for us is bird's eye view. You look above the vehicle in Euclidean space, you reconstruct a model of the world in 3D from a group of sensors, one model. And that tends to generalize better than treating them in isolation or not taking into the 3D modeling aspect into account. So it helps. And then we also produce often intermediate outputs in this bird's eye view. And they can be things like 3D objects, attributes, and so on, but they can also be more non-parametric representations, such as occupancy grids with probabilities for less shape defined objects, like for stuff. And why do we do these intermediate outputs? So there's reasons. Work before has shown that they typically improve generalization, even of the planet. Once you have the intermediate result, you can analyze your plan and validate that it does reasonable thing relative to your model of the world. And some of these outputs are also useful for building your own simulator and driving it as well. And there is another interesting point is that the sensor representation is extremely high dimensional. And through the perception stack, what we do is significant compression of this data. And then what we found is you need a lot more data or sequences of behavior. Because in one scene, maybe you have one interesting behavior or not, and you may have over the frames and 10 hertz, say, 20 seconds, 200 objects. You have tens of thousands of examples of objects, and maybe one interesting interaction. You want to, the intermediate representation can be helpful for data compression. And the cons, of course, as well, now we need to design these features in this representation, and we need to label them, and it can grow complex, and which features do you put in? That said, it's still popular, and I think necessary in some shape. Here I show an example. It made it on Reddit at some point. Someone posted, hey, Waymo understood there's a policeman and gave a bunch of instructions. And we are waiting until, and you can see above is a representation that we've talked about before and published blog posts about. We have these pedestrian key points that are helpful in understanding the gestures and the poses of people. So here you could see the policeman eventually waved us to go, and we went. Right? So we need to understand the guidance of policemen and construction people in order to be effective in the environments we drive. And there's some relevant research on similar topics, and even a challenge in our open data set for those interested in pedestrian keyboards. So let me talk first. Now that I presented this high-level architecture of what makes a perception agent, I will talk a bit about the first part. So as you create this bird's eye view representation, you want to process the information with machine learning model to generate useful features for planning and prediction. And the bird's eye view has a problem, which is that it grows quadratically with distance, because the volume of the space grows quadratically with distance. So your grid becomes larger, and your processes slow down, and you have difficulty doing real-time processing. And so we want to improve on the traditional solutions. Well, first, we want a transformer model, because they have great scaling capabilities. And second, we want to improve on traditional solutions. And for processing bird's eye view features, there is two typical solutions. One is dense convolution, so you have maybe 3x3 filters, and you process several layers of that to obtain better features. Or you have sparse convolution, which only applied where you have vectors or lidar points or in that space. But then sparse convolution is incompatible with TPU and is unable typically to pass information across point islands in the empty space, which hurts your quality. And so we published maybe over a year ago architecture called SW-Former, which does propose an effective bird's eye view processing architecture that keeps that does not have a quadratic dependence on distance while keeping top-notch quality. And this architecture is inspired, for those that work in computer vision, by a model called Swin transformer that is used to process images. It partitions images in patches, applies transformer layers to patches, then repartitions images in patches. And we do something similar here. But what we take is a set of sparse point clouds as input. And in the paper, they are generated in areas where we have LiDAR observations. But this is a general architecture. It can be applied to things other than LiDAR as long as they're sparse. So once you do standard processing on LiDAR points in this bird's eye view and form pillar features that are sparse, then we start partitioning that sparse top-down view into 10 by 10 patches. And these 10 by 10 patches are processed with our SW-Former block. Then we repartition in different 10 by 10 patches, so the overlaps are different and different areas of the space are processed. We keep upsampling several levels, and then we merge the information back from coarse to fine using FPN, feature pyramid network style aggregation. But in these SW-Former block layers, everything is still kept sparse. So what we have is attention on sparse 10 by 10 patches that was optimized to be really, really fast. And I think for more detail, and there is additional details in this work that ensure that the whole processing all the way through to the prediction head is done in a sparse representation. And once that is, and to details I refer you to the paper, but what happens is we show it is actually possible to have a purely sparse architecture that matches the state of the art. And at the time it actually established the state of the art, this is the Waymo open data set on the task of LiDAR object detection. This architecture was state of the art in quality, while much faster than alternatives when implemented correctly for the high quality regime. And this is what it looks like. So this is an example of a model like this working with a LiDAR, high definition LiDAR. This is some highway sequence. You can see over 200 meters. This is processing one frame at a time, so nothing particularly smart for vehicles. And you can even see some interesting vehicles like a Class 8 truck behind us and so on. And because you have a LiDAR, it looks awesome at night, because at night you don't see much here in this image. By the way, if you look carefully, you would know there's a collision here. It's over there, but we see it down the highway even better than day. So this is just a simple LiDAR detector illustrating this, the efficiency of this architecture. Now let's switch to behavior modeling, the second part of the diagram I showed. And first, let me describe how behavior model typically is addressed in the literature in our domain. So you have a set of scene elements. That can be the world state is comprised of agents, traffic lights, road networks, so a bunch of lanes. And you have all of these entities. You process them using a deep neural network. And then for every agent that you observed, including potentially yourself, you predict k trajectories. So it's a discrete set of trajectories. These are possible futures. People are non-deterministic. They don't drive the same way. So it's a probabilistic output. And then for each trajectory, you have multiple seconds, 4 to 8 seconds, or in the academic data sets. And you can have poses maybe every few frames, and uncertainties, location uncertainties with these poses. Essentially, what we call this thing is like a Gaussian mixture model of trajectories. And this is what the outputs look like. So if you look at the vehicles, the different futures are colored. So 0 second to 8 seconds with some model of ours. And then you have the more saturated the future is, the more likely it is. So that just kind of to show you what kind of predictions a model like this generates. So we did this work over 5 years ago. And now what we've done recently is we upgraded significantly the architecture to use transformers, surprise. Right, and there's a paper called Wayformer that describes that architecture, but it's fairly generic transformer architecture with relatively simple set of primitives of how to apply attention, and searched properly, we can get state of the art to encode all of this, and then you have similar Gaussian mixture model predictor, but now it's done using a transformer cross attention head. And so it's great that you can have fairly straightforward model like this to do the task. Before, people used to do this with a lot of custom smarts and tweaks in the architecture. Now there's relatively few parameters, and you can explore them and scale it relative to the data. And so now, OK, so we have this model, but there's another issue. So the other issue is, typically, if you do k trajectories per object, right, then given the scene, here's k things you can do. That's what we call marginal a posteriori predictions. They're suboptimal in the following sense. They don't model relationships between agents. They just model what the k modes for yourself, independently of what others do. This is an example. If you look at the cyan vehicles here, is it the cyan ones? Yeah. There are two modes that got predicted. They're each likely by itself, but they lead to a collision. And if you model the interaction, then collision actually is very unlikely because people react to each other. But if you ignore the other players, that's perfectly reasonable behavior for everyone. And so some time ago, we did an interesting work called joint future prediction to address this. And joint future prediction says, well, the future of possible, if every agent has k options, and if you have n agents, you have an exponential set of futures. What's a good way to model an exponential set of futures? Well, it could be a probabilistic graphical model. And this brings a bit to Ben Taskar, because when we were designing this model, this was some aspect of it was directly inspired by a discussion we had with Ben in 2009 at the CVPR conference. So he was telling me about his ideas, and those ideas inspired at least a feature in this paper. So how does this work? So you have a deep neural network, and you predict these marginal trajectories for every agent. But now we're going to add pairwise potentials between the agents in some graph, forming a probabilistic graphical model that we could train and backpropagate through. And we do maximum likelihood. And if you create a loopy graph, then you can use loopy belief propagation. And if it's a tree-shaped graph, then you have exact inference. And so you can just backprop through all of this and model joint futures, at least with some approximate graph representation. So, and you can use different graphs. So you can have no graph, that's where we started, or you can have fully connected graph, and then you need to do loopy belief propagation, approximate inference. But at least certain types of graphs seem quite well fitting. So here you can do AV, autonomous vehicle-centric graph. You just connect the autonomous vehicle to every other agent, and you say we mostly worry how we interact with the other agents. We don't worry as much how they interact. And there's the last thing you can do, and here first you predict the marginals for everyone. Then you see which marginals interact or overlap. And then for those, you add secondary edges. And this was similar to ideas Ben had, how he builds inference from marginal clicks to pairwise to higher order clicks, but very selectively depending on the interactions. So we built this. So we could do these sparser graphs, but not necessarily tree-shaped. And then we evaluated it. I don't want to go into too much detail here, but essentially there's metrics where you check whether your predictions were close to the ground truth, and you have k choices typically, and at least one has to be close, and then you see how close it is. That's called mean AD metric. Out of, say, 6 guesses, the closest how far it was. And the joint version is you do it for pairs of agents. So both predictions, you take the closest guess for both, and you look the joint loss for, so making sure that pairs of things match well. And so in this case, you can do a lot better in predicting interactions with the vehicle. So here, smaller is better. And the dynamic version of the graph does equally as well, or even better. And this is another metric which says how often do you predict vehicles hit each other in your predictions. That shouldn't happen much. So typically, lower is better. And again, this is evaluation just of us with the other vehicles. But what the dynamic thing lets you do is you can handle pairs of other agents, which otherwise are not addressed. You can handle them dynamically as you go. And does seem to add an interesting feature, especially for simulated agents or others. So it's pretty cool that we could do graphical model work in DeepNet world. And at the time, it actually was state of the art for a challenge we had on interaction prediction, which is also pretty cool. This is the JFP, Joint Future Prediction. And then we are in 23, and language models are hot. And then you think, OK, why is driving not a conversation? Actually, we always thought it, but it was time to revisit. So if driving is a conversation, right? Can we do a LLM-inspired model? So what does that mean? Well, let's make discrete motion tokens. So they're like letters or words that make up your trajectory. So you can create them by clustering the trajectories you have. And then can we apply causal decoder the way the decoder models produce language and see what happens, how good can we be? So full joints. We're predicting full joint trajectories. It's as if all the participants are talking words to each other, right? And we're predicting that. And so you can have some sequence over time with different tokens. And to train it, we train it with teacher forcing. So you feed in the previous step, and you try to predict the next in this model. And then at inference, you just roll out these futures, giving the context of a set of previous tokens and predicting the next token for each agent. And then you take all these tokens and craft a future, and you can maybe sample several futures to produce a distribution of possible futures. And if you look at this, it predicts fairly well, better joint predictions than the marginal method, which otherwise says vehicles run into pedestrians a lot, and here they're interacting in more realistic ways. And this method is also state-of-the-art, maybe on slightly different metrics than the JFP method, but the second set of metrics are more sensitive to long-tail cases. So another ingredient for scalable ML stack is distillation. Right? Distillation is this technique to improve model performance by distilling from a teacher or an ensemble of teachers. And this is a known approach, but we explore it in a paper for behavior prediction. And on smaller academic data sets, like the ones available for behavior prediction, distilling from ensembles is particularly appealing. So ensembles allow you to scale model capacity while limiting overfitting. And so what we do is first we train a large ensemble, and you can see how, so blue is better higher, and orange is better lower. So you can see as we train larger and larger ensembles of predictors, quality gets higher and higher, but then we don't want to pay the cost of all these networks running in parallel. So now we're going to run the ensemble. We're going to average its outputs, and then we're going to distill, train the student model to produce these outputs. And when you do this, you get state-of-the-art on the motion challenges. So here you can see the behavior of the ensemble, which when you go to 20+ model establishes, so state-of-the-art on the data set overall before this paper is the blue line. And when you make the ensembles big enough with our models, eventually you achieve state-of-the-art. But then you can take that state-of-the-art and you can distill it to small models. And these small models are dramatically higher quality and in some cases much faster than counterparts that you would do without distillation. And on this metrics, it's flipped, so lower is better. and you get a similar effect. So after distillation, with something that's very state-of-the-art, even though slow, you get gains. So distillation is a helpful technique. Another technique that we've worked on that is important once you have intermediate representation is auto-labeling. You don't want to label too many scenes with boxes. You want a machine to label most of them for you. And when you auto-label, you have the benefit compared to running on board is you see the future. So you see past and future for a long time. So you can do much, much better than simply online style processing. And so we did an algorithm. That was an old one. Maybe it was first paper of its kind doing this. This is a result of that algorithm. The quality of the bounding boxes produced, actually it made the Waymo open data set, this algorithm. It's described in the paper. And the main idea is that, I don't know if you guys can see, after you apply a detector on a bunch of frames, you track every object in the detections. You collect the full track, and if it's static, you apply a model to just reconstruct the full bounding box. If it's dynamic, we have a model that takes the full track of the vehicle and processes it to give you the final bounding box in the full tube, space-time tube for that object. And when you do this, you get accurate results like that. But what's new now is that in 23, we tried to improve on this algorithm. And we said, OK, well, now we have behavior prediction. Can we leverage the power of behavior prediction to improve on potentially brittle case when you have to track this object with somewhat heuristic tracker? Can we use behavior prediction to carry information across time? So it's, in a way, it treats behavior prediction or motion prediction as another modality. And the way it works is, so you break a long sequence into subsequences, maybe 10 frames each. You then process each subsequence. You run detection. You track the objects there locally. And then you motion forecast from that sequence to back or forth in time. And then these predictions, you pass to the other sequences. So they start cross-pollinating each other. And this cross-pollination is essentially these, what we call mother points. They're virtual points that got sent to you. They're not lidar points. They're just these sparse points that are sent to you about the center of vehicles from other frames. And now we have another domain which has, say, lidar points and virtual mother points. We can put a detector on top of that, and we get significant improvements yet. And it improves these various 3D detectors. It's generic approach. You can augment any specific lidar detector and improve it. And it can do things like objects stop disappearing when their points go away, and you also see it a lot longer ranges and fill in gaps. So it creates a very consistent, almost close to ground truth representation of the world without as much of the perception noise that's present on board. So that's very useful for auto-labeling. But auto-labeling does not do everything. It's really good at more common cases. For rare examples, you still want to mine them, upsample them, and in some cases, augment them. Right? I mean, the rare examples you just don't have enough of. So those are the most valuable to augment. And for mining rare examples, we have a couple papers I would suggest you go read. But for augmenting them, this is a work from this past year. It works. It's also implemented for LiDAR, but it's generic. If you can reconstruct object in 3D, it can be applicable. Essentially, you take a LiDAR crop of an object or detection, and you can modify it in a bunch of ways to create variants of it. You can crop, you can stretch, you can cut, and you have a set of parameters now that augment. And what's nice about this is they're very natural, realistic. In 3D, it's easy to define natural and realistic augmentations. But these augmentations still have parameters. So this space we just created has around 30 parameters. And we had been doing work on how to search this space. Someone needs to set all these parameters. And how you set the parameters depends on your model, how big its capacity is, and so on. So you want to do this automatically. And traditionally, we had fairly complex ways to do this. So we had population-based augmentation. There's different seeds that keep producing novel models that cross-pollinate each other based on the success in past timeframes and so on. But this work shows how the whole thing can be done a lot simpler, which is easier to use. So the idea is to define a simple search space. And then the question is, what is that? So you factorize. You say every different augmentation will model by itself. And so for each augmentation, we do proxy search for just two parameters, probability of applying it and some sort of magnitude parameter. And once we do this for every augmentation out of the 10-ish or so that I showed, then you normalize and center these parameters to roughly the same scale. And then once all of these are aligned and centered around the same PMM values, so P0 is P0 across all of them, or P05 really, then you just do grid search in global space. You search for the PMM across all the augmentation operations, a single one after you've aligned them. And that seems very effective. So it's actually contributed to state of the art. It made this W former model, for example, work yet a lot better through augmentation. And this is true. It's generic to most models. But it offers significant gains. And the gains are the strongest, again, for the rarest examples. Something else that's endemic to our problem, which is that we're building agents. And for agents, they're susceptible, as I already discussed, to covariate shift. So if you want to have an agent policy, and you learn a policy, especially if you do behavior cloning, just clone the behavior every step at a time of an agent you observed, then as you start running this policy in an environment, it starts making errors, epsilon errors, that take you more and more out of domain, causing you to potentially make bigger and bigger errors. And this is a problem for robust agent models. And so we've done work on doing more sophisticated imitation or reinforcement learning that induce a better robustness to covariate shift. And one of these work is from this year. It's called Imitation is Not Enough. And it explores the trade-offs, so the kind of mutual beneficiality of imitation learning and reinforcement learning. So the benefits of imitation learning are you learn realistic behavior. You don't need to define a reward. You're just imitating what others did. But it has relatively poor behavior in out-of-domain cases, that you just don't have as much in your representation, in the data you collected. Reinforcement learning, on the other hand, requires you to design rewards. But it has more robustness to the long tail, where it did not have direct data. So we designed a simple algorithm that we called BC-SAC, like behavior cloning SAC. And essentially, it has these two losses. So when you're in distribution running an agent in the blue zone, you apply two losses. One is imitation, and one is RL loss. The RL loss is don't collide with other agents, don't run out of the road. Yeah, this is that loss. And when you have in your sample, as you run on policy and the agent go outside of the distribution in the red zone, then you only apply the RL reward. The imitation does not apply. You've deviated. So when you do this algorithm, we do indeed see that there is increased. So this is naive behavior cloning, doing nothing special to be robust to covariate shift. And it does pretty well, but these are the hardest examples to easier and easier examples. For the hardest examples especially, so MGALE is an imitation learning approach that uses a discriminator to induce some robustness to covariate shift. And this is the BC-SAC algorithm we proposed that mixes imitation. Very simple one, actually, that mixes imitation and RL. And that one is the most robust in our benchmark. And this is some video of using or not using the algorithm. This is MGALE, it's imitation learning algorithm with the discriminator. So here, when a person comes out of the vehicle, we still swipe way too close to them. The agent does. Here, when we run also with RL losses to not collide, it hedges bets and swerves further away from the person, just in case. Because from the RL loss, it learned that it may be beneficial to be further away and not induce a collision. So there's a way to shape these imitation further with targeted rewards. Last thing I would talk about is leveraging vision language model or large language model knowledge. This is a relatively new topic. I think it's quite popular in many domains. These models know a lot of things about the world. They're trained on internet scale data, both text and images, maybe soon video. And what these models can do is understand fairly complicated things. You guys may have seen this. This was very cool, right? This is the stop sign, and you ask, it's Wednesday at 4 p.m. Can I park at this spot right now? Tell me. Yes, you can park for 1 hour starting at 4 p.m. That's pretty cool, right? That's useful. We need to understand signs sometimes. Sorry?
That's super intelligent.
It's cool. Well, we want it if we can have it, right? And this is another example. So you give this picture and you say, I'm driving on the street. This is what the front window is what I see. Tell me what's happening and what I should pay special attention to. And tell me what I should do and specify the reasons. And the VLM says, you're driving on the street and see a car flipped over on its side. There are firefighters and police at the scene. You should pay special attention to the traffic around you and slow down. You should also be aware of the possibility of further accidents. You should call 911 and report the accident. I mean, some of these are maybe actionable. Others maybe less so. But still, you should also stay out of the way of the emergency vehicles. So these are good set of advice. And we want more of this knowledge embedded in our agent, ideally. So, yes?
The car is not flipped over on the side.
Yes, well, it's slightly on the side. So that's what the VLM said, just an example, right? So in any case, there's interesting questions in this space, and we have a few projects ongoing, which unfortunately we have not made public yet. But we have published some work in this space that I will show that relates to approaches for getting some of this knowledge that these models have. One of these works was earlier in 23, its goal was to extract the knowledge out of vision language model and use it to train a 3D model to detect a bunch of objects without ever having to label anything, right? And the main idea was the fact that since we can cross-correspond LiDAR to images because the sensors are calibrated and we know the function, what we can do now is we can annotate every LiDAR point with embeddings from the image from this VLM. And we can do a little bit of surgery. So one is we can exclude all the categories that in the image are understood to be roads, buildings, and so on. Let's say we want to annotate only moving agents. And then we also had proposed a way to cluster blobs of LiDAR and produce boxes. So once you have boxes and you have these embeddings, you have an annotation of the scene derived from the vision language model. And then we train a detector just on the LiDAR potentially, but it can be also image LiDAR to distill the information from before. And so from these tracklets and features, now you train a model to, without any labels, just produce you the scene at the top with boxes and semantics, actually. VRU is vulnerable road user pedestrian. You get boxes and you get static objects. You cannot do these things if you're just tracking blobs because a lot of the things now this model makes you detect are not even moving. So it's a nice result. One can also leverage models like large language models for behavior modeling. And generally, in this case, though, first what I'm showing is there's other cool technology like diffusion models that is part of this generative AI wave lately. And we have diffusion model of various kinds. This one creates variants of a scene. So you specify maybe the road graph and some agents, and it fills in the rest in plausible ways and evolves them over time. So this is a model we have. This was some log data with some objects. Sorry for the small boxes. And here we generate variants of the scene with different traffic from this model, including the motion of the traffic. So essentially what this does is you specify a set of constraints, and then you run a diffusion model, and the diffusion model fills the rest. But these constraints are not that easy to define. So one thing that we tried is to use an LLM. Right? So you can show it examples of constraints and renderings subject to constraints. And given that prompt of examples of how language queries are mapped to constraints, it starts generating constraints for a diffusion model that can be done with language. So here, instead of saying there should be a vehicle in point time 3 at position X, or these two vehicles at some point need to collide, you can say things like this. Generate constraints for agents where they form a formation around the autonomous vehicle and travel along with the autonomous vehicle. All agents are cars, except the front two agents should be motorcyclists. And the LLM generates a configuration like that, which is pretty cool. Right? And there are the examples similar. So there is significant abilities in these models embedded that can be derived and potentially help facilitate creating scenes on demand. So there's many open questions in this space. And actually in the community, there's a lot of papers that come out with people starting to explore it. I'll just go through a few. One of them is what are good VLM architectures or similar architectures for autonomous vehicles, optimized for video and other sensor modalities, and maybe with better spatial reasoning, which so much matters for us. I showed you that we have intermediate formats of certain kinds, like you have a model of the scene with lanes and boxes and maybe other things. Now, how do we reconcile those types of formats with language-based scene descriptions? And those language-based scene descriptions are more closely aligned with the knowledge in these models and can enable things like chain of thought. How do we reconcile the two? Do we need both? Do we need a mixture? Do we switch to just the language description of the scene, but then which one should it be? Is it super long language? How do we process this? And language condition planners, we want to give them instructions or create scenarios like the diffusion one I showed you, and maybe we want them to refine existing scenarios, or descriptions of what you're doing or plans. And for us, always very relevant, how do you preserve these capabilities given limited onboard compute? Because otherwise, it's all great, but how much of it can you actually leverage is interesting. And many, many more questions. This is just some off the top of my head. I want to encourage more of you to consider exploring and doing research in our domain. I think it's a fascinating domain with no shortage of exciting questions and great applications. And yeah, that is the summary of my talk. I presented some ways towards building a scalable ML agent for driving in this case. All of these have helped us in various settings to learn more from our data. And thank you for the honor again. And if you're interested to learn more, we have data set with certain problems that we continue expanding. We have a set of research published on the Waymo research page. And you can also consider joining us. So thank you very much.